Okay, let's go ahead and get started. Good day, everyone. I'm Jason McDowell, Chief System Integration Officer for the Energy System Integration Group. It's nice to see everyone here today. Would love to warmly welcome you to one of our ESIG monthly webinars for October. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working groups and task force activities, and producing technical resource materials across the industry. ESIG also serves in a leadership role with the Global Power System Transformation Consortium, or the GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. ESIG leads the first of 5 pillars, and that drives the research agenda for the system operators. We are well into the preparations and just around the corner from our fall technical workshop in Providence, Rhode Island next week. And I'm excited to share that we prepared another great lineup of tutorials and technical sessions there, and I hope to see you there. Further information can be found at our website at esig.energy, where the final agenda and registration information are posted. Our workshops and monthly webinars are open to everyone, so please feel free to register at any time at the ESIG website. If you're new to ESIG, and I strongly encourage you to follow up with us, especially if you like what you hear, and I think you'll be very pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces, and you can find us more on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Before I hand it over to today's star of the show, I just wanted to share a few logistical items before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A today, we're using Slido platform. So slido.com is the place to go, and enter code ESIG16, ESIG16 as the event code. The instructions are also at the bottom of the screen. Everyone will see a thumbs up button next to the questions to allow you to cast a vote and help prioritize the questions. We'll plan for about 10 minutes or so at the end to wrap up with question and answers before we hit the top of the hour. An email link will be provided with the video file that has been posted, and we'll also plan to provide short responses to any unanswered questions to the webinar. Today's topic offers a global perspective and a global update on grid forming projects and specifications. This is a topic of high interest and importance around the world, and the transition to a system dominated by inverter-based resources. A year ago, a similar webinar was held comparing grid forming specifications at that time. This webinar will provide an update based on the latest developments of grid forming projects and specifications, including those most drafted from MISO and ENTSO-E, as well as remaining challenges in testing and conformity assessment of grid forming capabilities. Here to talk with us today about it is Julia Matevosyan, Chief Engineer at ESIG, who has over 20 years of experience in the power industry and over 10 years of experience with ERCOT prior to joining ESIG. Julia takes a very active role in many leadership activities across the industry, including at NERC, at IEEE, at CGRE, and GPST, and many others, and is very well known for her work internationally. It is my great pleasure to welcome Julia here today and share this perspective with us. Just a short reminder once again to use Slido at slido.com with the event code of ESIG16 to ask your questions. And without any further delay, it's my great pleasure to introduce Julia. Julia, I'll turn it over to you now.
Great. Thanks, Jason. Thanks for the introductions. So I'll just move on the next slide, and I have a little bit of outline of what I'm going to cover today. So as Jason mentioned, about the same time last year, we held a similar webinar. So I decided I'll skip all the background about why we're talking about grid forming, what's the purpose, what's the role of grid forming in the future of energy transition. And I linked up the webinar here. So once the slides are posted, you can just go back to that webinar and see the beginning of it for the motivation. And so then I'll talk about just the definition of grid forming. I think it's important to establish a definition in every venue where we talk about grid forming. And then I'll talk a little bit more about what happened since the last webinar in terms of new specifications and testing landscape. First at glance, and then I'll dive deeper into some of the grid forming specifications and testing documents. And then as time allows, I'll try to cover as much as possible, but at some point I'll just jump to short discussion of incentives. So some of these grid forming specifications are mandatory requirements, and then some of them are incentivized through some market products. So I'll talk a little bit more about that. I'll spend a little bit of time on grid forming battery energy storage system projects that have already been built or currently under construction, and then conclude and hopefully leave some time for Q&A. All right. So first of all, grid forming definition. I picked the NERC definition, and that's the one that kind of we've been using at ESIG as well, and in the previous webinar. So grid forming IBR controls maintain internal voltage phasor that is constant or nearly constant in the subtransient time frame. This allows inverter-based resource to immediately respond to changes in external system and maintain IBR control stability during challenging network conditions. The voltage phasor must be controlled to maintain synchronism with other devices in the grid, and must also regulate active and reactive power appropriately to support the grid. So basically what it means, if there are changes in external voltage magnitude, then there will be nearly instantaneous response in reactive current coming from grid forming inverter-based resource. If there are changes in voltage phase angle, there will be instantaneous reaction in terms of active current provision from inverter-based, from grid forming inverter-based resource. So that's kind of these two expectations, and you'll see it in the specifications as well. There are many variations of both grid forming and grid following controls. Both are subject to physical equipment limits. And when we talk about grid forming specifications, we need to keep in mind that for the most part, grid following IBR requirements also apply unless there is a conflict, and then it's discussed separately. So potential use cases for grid forming controls is to support weak grid operation, so that grid following resources in weak grid areas can continue operating stably. Provide damping of voltage and frequency oscillations, resisting voltage phase angle change, or sometimes it's called phase jump response, resisting frequency change or limiting rate of change of frequency, and this is viewed as a substitute or supplement to inertial response that's provided by synchronous generators today. Fast fault current injection for balanced and unbalanced faults, mitigation of subsynchronous control interactions, support of islanded operation when required, and black start operation when required. So this kind of first few functions, that these are seen more of a core functions of grid forming, whereas this last two are more of an optional and are system specific. Right. So now specifications landscape at glance. I will not go through everything from 2019. I talked about it in the previous webinar. I'll focus more on what happened in 2024. So in the beginning of 2024, IEMO released testing specifications. So this is to clarify how capability that they identified in the voluntary requirements for grid forming should be tested for. So basically we talked about in 2023, IEMO already released the specifications for grid forming resources, whereas the second document in the beginning of the year 2024 talks about how to test for this capability. Then VDE FNN, this is a draft document in Germany, and this one is it's more for grid forming resources that will be providing what they call momentary reserve, and this will be procured as a market product, and I'll talk more about this. But basically, this is specification for resources providing this momentary reserve. And this serves as supplement, or in some instances, a substitute for the previous VDE FNN specifications for grid forming that were released in earlier years. Unify have published the second version of their specifications. Fingrid, who is system operator in Finland, previously in 2023, they have published specifications for studies for batteries that are going into WeGrid areas, specifying grid forming capabilities just in those cases. And so that previous document was really just a study requirement. It wasn't part of the grid code. So what currently is happening is that Fingrid is trying to include this grid forming specification for batteries into actual grid code document, and there is a draft out there. It's unfortunately just unfinished, but I heard that by 1st of November it will be published in English. And then MISO published a draft white paper with specifications for grid forming batteries. ENTSO-E, who is Association of System Operators in Europe, has published a draft version of requirements for generators, or RFG 2.0. That draft version was approved by the regulator ACER and now is with European Commission for approval. And so that one is also defining grid forming requirements for different resource types. And then last but not least, ORCAT also has released specifications for testing for grid forming batteries just recently in September this year. I'll talk a bit more about which of these specifications are requirements and which are voluntary and which are through markets in the later slides. And then just yesterday, as I was preparing for this webinar, I found another document from National Grid ESO. Sorry, they are from October 1st. They're called National Energy System Operator. So this is a system operator in Great Britain. And they were one of the first ones to publish grid code requirements for grid forming in 2021. So this NGSO document that you see here. But they also now have a document that is for, it's a guidance note for grid forming plans. So it's basically how do you test and prove that you have grid forming capability in accordance with this requirement. So this is another document that's there and specifies that. One thing I wanted to mention, as I track all these requirements, I do have we have a webpage at ESIG where we kind of keep up to date links to all the documents. So if you go to this link here, you can find all these documents that are on this timeline. We try to keep it up to date. And if you see something that's missing from there, please let me know. I'll have my email address at the bottom of the last slide. Also, before I move on to the next slide, just wanted to mention that everything that in the presentation is my interpretation of requirements as I read these documents. And so if you need actual details and specifics, I advise you go to each specific document and you'll look it up and double check what I have there. This is just an outlook of where these requirements are coming from. So initially, I think as grid forming technologies just started, being of interest, there was more of research organizations and industry working groups that were focusing on grid forming specifications, trying to define what are the capabilities that are needed. But then gradually system operators and regulatory bodies became interested in publishing specifications. And so here you can see this kind of gradation between two different groups. And then some of them are already published and some of them are in draft form and some are still planned. So these plans that you're seeing here are just based on some presentations that I've seen before or some conversations with the stakeholders. The requirements differ in level of detail. So some are more high level, some are more deeper in the weeds and define numerical parameters. Some are functional specifications without accompanying testing requirements. Some are just test requirements, and some comprise both. Some documents are split into core and advanced capabilities that are required, and some are not split. As I mentioned, some are voluntary and incentivized through markets or some other products, and some are mandatory. These requirements are in addition to existing grid following requirements, and unless there is a conflict. And some requirements apply to all types of resources, others apply to all inverter-based resources, and some are just for battery energy storage. And why is this difference? I have this cartoon. I also had it in my previous webinar. It's just because I really like the analogy. And this is to say that for battery energy storage is most straightforward to be grid forming as compared to other inverter-based resource technologies such as PV and wind. And so it's like making battery grid forming is like teaching a kid to ride a bike, and so it's relatively easy. Making PV grid forming is like teaching a monkey to ride a bike, and making wind grid forming is like teaching a bear to ride a bike. So these two categories, basically, they don't have an internal storage that is needed for grid forming to provide grid forming capability as at fullest, and so they will require some kind of like energy buffer or backing down a regional resource. For wind technology, it also has implications on mechanical structure, mechanical stress. And one other thing, why battery is also, if you look at interconnection queue, at least in the US, there is a lot of interest in developing new batteries. And on the other hand, also other inverter-based resources are coming in. So it seems like asking for grid forming in battery is a lower hanging fruit and is a real window of opportunity where we can, by jumping on it now, we can maybe get some of this capabilities, stabilizing capabilities, and support additional wind and solar in the future. All right, so I'll move on to the next one. I looked at all of these requirements, and one good thing about it is that functionalities that are required are pretty common in all of the specifications. So is this like response to voltage phase angle step, response to voltage magnitude step, limitation of ROC-off, some of them define it as inertial response. You'll hear the details of this. Active power sharing behavior at current limit, counter imbalances, counter harmonics, provide damping, no control interactions, and ensure interoperability between all inverter-based resources, operation in low system strengths, operation in an island, and then resynchronization back to grid-connected operation, and then surviving loss of last synchronous machine. And then I have this black start capability kind of as a separate here in a different color. None of the specifications requires black start capability as a core requirement. Some specifications just talk about black start capability as on per need basis. And recognizing that additional hardware considerations will be needed here. All right, so I'll just talk about some of these requirements a bit more in details and trying to compare what's there. And again, I'll see how far I can get. I'll reserve about 10 minutes to talk about incentives, but you'll have slides and you can look through other requirements later on. So response to phase angle step is basically inherent in definition of grid forming. So as you can see, most of the requirements that we have reviewed ask for nearly instantaneous active power response to voltage phase angle step at point of interconnection. And that basically looks at injecting or absorbing active power to oppose the change in voltage phase angle. Initial response time is defined by national ESO as 5 milliseconds, and then IEMO also specifies it the same way, but they refer to an ESO requirement. FinGrid says within few milliseconds, And then FinGrid requires full response, while others specifies 90% of response in certain time. And so ORCOT says 1 cycle, FinGrid and VDF, and then say 10 milliseconds. IEMO and MISO specify 15 milliseconds. So this is to full or 90% response. ENTSO-E RFG says that relevant system operator in coordination with TSO shall specify temporal parameters and dynamic performance regarding voltage stability. And what I didn't mention in the beginning as I was showing landscape, the ENTSO-E RFG requirement draft is out there, but there is also another document that is called First Interim Report, and this one is trying to specify what these high-level requirements in the ENTSO-E RFG mean, and provide kind of more quantitative specification. And I think this is the first step into the implementation guide document that will follow once the ENTSO-E RFG is approved. So some of this, where it says TSO shall specify, this first interim document already provides some recommended parameters. And then National Grid also defines 60-degree phase jump angle withstand. I think National Grid is actually the only one that talks about withstanding a phase jump. So this slide is just fresh off the press. It came from Wind and Solar Integration Workshop in Helsinki last week. And so this is showing what's required by VDE FNN. So as I mentioned, this document is specifying what grid forming resources providing momentary reserve have to do. And so it says that in the beginning, when there is a phase jump, there will be this, ideally, there will be this first response that is only characterized by effective impedance of inverter-based resource unit. But after that, there will be inertial response and damping. So this is the effect of this, what you can see in green. So this requirement is saying from this maximum response that you can expect in the beginning that is based on impedance, 50% of this theoretical response have to come from the resource that is providing this momentary reserve in the direction in which this reserve is provided. So basically, in this German market construct that is being proposed, the reserve can be provided either to positive phase jump or negative phase jump, or in both directions. So whoever is offering this service, they can choose. And so if they choose to offer this service, then then it specifies how it should be provided, and there are also testing requirements for that. And in the direction where they are not providing the response, still 5% of response is expected from the grid forming resource. So I'm jump to the next one. IEMO, MISO, and ORCOT and FinGrid define relatively similar phase jump test. So this is tested for short circuit ratio of 3, system equivalent X to R ratio of 6. There are different dispatch conditions that this is tested for. I won't read through the slides, but you can see it here. And then how the test is conducted, the angle of the voltage source behind equivalent impedance is decreased instantaneously by 10 degrees. A few seconds later, it's increased back by 10 degrees. And then the steps are repeated for 25, plus minus 25 degrees. In MISO and ORCOT, IEMO and FinGrid do plus minus 30 degrees. And IEMO also does a test for plus minus 60 degrees. National Grid, in their testing specifications, they test at 5 plus minus 5 degree steps up to 50 degrees phase jump. And in the criteria, what they're looking for is instantaneous power response to oppose the angle change for each of this 10 degree voltage phase angle change, as long as current limit allows. There is a definition, as I mentioned, for the 90% response time. So this is what's being looked at in the tests. Active power has to settle to pre-disturbance level shortly after each phase jump. If active power reaches or current reaches limits for 60-degree change, the plant should return to pre-event power levels in a stable manner. That's what AEMO defines. And then any oscillations shall be settled, and any distortion observed in phase quantity should dissipate over time. So in response to voltage magnitude step, again, this is by definition of grid forming. The expectation is that there is nearly instantaneous reactive current response to external voltage magnitude step to oppose the change in voltage. And it's basically the same across all of the requirements. It doesn't use exactly the same language, but that's what the requirement is, pretty much the same. The initial response time of less than 5 milliseconds is defined by national grid and AEMO, and few milliseconds by FinGrid. Again, FinGrid defines time to full response. Others define time to 90% response, and times kind of differ from one cycle to 50 milliseconds. One thing I haven't mentioned is that FinGrid, the response times that they currently have in the study specifications for batteries are just recommended values, and it is expected that in the grid code, these values will not be specified. So they basically will require instantaneous or nearly instantaneous response, but will not specify the time for full response. And again, ENTSO-E leaves it to national system operators to define specific parameters of this response. Again, there is a step test defined in ORCAD and FinGrid at different short circuit level conditions, different dispatch of a tested device, and magnitude of the voltage source is changed instantaneously plus minus 3% in ORCAD and plus minus 2% in FinGrid, with a few seconds between the tests. In the criteria, what's expected is instantaneous reactive power response to oppose voltage step to each of the steps in voltage, with initial peak reactive current change to at least 0.03 per unit of rated as defined by ORCAD. And ORCAD also defines that reactive power should not return to pre-disturbance level within at least 6 cycles. Response time to 90% is defined by ORCAD and FinGrid. Kind of there is a pretty big difference here. 1 cycle for ORCAD, 1 second for FinGrid. Again, for FinGrid, this is recommended value. Any oscillation shall be damped, and then final reactive power after each 3% step is expected to reach maximum reactive capability in the effort to regulate voltage in the in the POI to 1 per unit. That's what ORCAD defines. Interesting thing I wanted to point out is that FinGrid actually is the only one that specifies side tests for all the documents that I've reviewed so far. And so basically for the step voltage step change, they will have a test where they will change topology of the grid. And so that will result in voltage magnitude change, but also voltage step, phase step. And acceptance criteria is that it's required to perform according to requirements. And they will also do phasor domain and EMT domain model validation based on those test results. National Energy System Operator also defines fast load current injection. So they expect reactive current to start rising within 5 milliseconds as voltage falls below 0.9 per unit. And deployment of full response shall be achieved within 30 milliseconds. And so what you can see here is the response if resource has only 1 per unit capability for this fast fold current injection, or if resources has short overcurrent capability of say 1.5, then what's expected response would be. Again, National Grid doesn't require oversizing for provision of grid forming capability, but they require to announce what kind of capability you have. So if there is a short-term overcurrent capability, the generator owner will have to specify it in the documents. Then limiting drop-off. It's again, this response is expected by definition of grid forming. So most of the operators define it as inertial response from grid forming inverters, which should be inherent and not calculate frequency and not be like controlled type of response. And it needs to provide nearly instantaneous injection in active power in response to grid disturbance, such as load or generation trip. Unify and FinGrid requirements do not explicitly call it inertia, whereas others do. Initial response, again, National Grid, ASO, and IEMO expected within 5 milliseconds. FinGrid specifies within few milliseconds. Full response in less than 10 milliseconds, defined by FinGrid. ENTSO-E RFG has similar requirements for over frequency for type B power plant modules and both over and under frequency for type B batteries. And then type C and type D power plant modules, they have to have this response both for under and over frequency. It also says that for type C and type D resources, relevant TSO may require provision of additional energy beyond what's inherently available. So at national level, they can specify additional storage capacity, basically, that is needed. And again, this is same here, that at national level, there will be a specification of temporal parameters and dynamic performance, which again, I believe is already there are some recommendations in the ENTSO-E first interim report. This is just a slide here for you to understand what's type B, type C, type D in ENTSO-E requirements. It varies by different countries, and it's by size of resource and connection voltage. So I'll just leave the slide here for you to look afterwards. If inertia is configurable, it needs to be tuned to network conditions, and that's the requirement by IEMO. Recognize that too high inertia constant may increase power oscillations in strong systems. IEMO also recognizes in the advanced capability requirements that a larger headroom and energy buffer can be defined. National ESO tests response for rock-off of 1 Hertz per second, and also they require withstand capability for rock-off of 2 Hertz per second. And then there is also this test for cumulative energy during rock-off as the frequency changes between 52 Hertz and 47 Hertz. This is again from VDE FNN. The resource under test is basically subjected to this different rate of change of frequency. So this is like a frequency event with different rate of change of frequency over time. And so depending on the direction where they offer this momentary reserve, they'll be tested for provision of inertial type of response. But also what's interesting is if they offer, say, in the negative direction, so during overfrequency, they'll offer to reduce the active power output. They also are expected to respond to this negative rate of change of frequency by injecting power back. So basically, if you have provided frequency response in a negative direction, you're also expected to provide it back in positive direction. Rock-off test, again defined by IEMO, MISO, ORCAD, and FinGrid, relatively similar test setup, a bit different dispatch levels. The frequency is ramped by plus minus 1 Hertz from nominal. At 4 Hertz per second in IEMO and MISO tests, ORCAD test at 1 Hertz per second, FinGrid tests at relatively small, 0.1 Hertz per second, and then stay at each frequency for 5 seconds before repeating the test. and 2 seconds defined by ERCOT. And then 2 more tests defined by Fingrid at different levels of rock-off. What's expected here is that plant active and reactive output should be well controlled. System frequency voltage should not oscillate excessively or deviate from steady state levels. Voltage settles at stable operating point when frequency is not ramping anymore. Active power should settle according to frequency droop and deadband settings. When frequency is not ramping and any oscillations shall be adequately damped. ERCOT requirements again defines equivalent inertia constant and explains how it is calculated in the test event. Active power sharing, there is no specific requirement for active power sharing except for in Unify, so it doesn't, like other requirements don't call it out. But in all specifications, in frequency response requirement, it talks about droop type of response. And so in the frequency response requirements, in island operation requirements, and the loss of last synchronous machine requirement to test, this is where it's being looked at and droop type of response is expected. Behavior at current limit. So this is relatively common for all of the requirements. So by definition, all of these requirements require grid forming to respond inherently and nearly instantaneously by injecting current in response to faults, voltage magnitude and phase angle jumps, frequency events with different characteristics. So it's like active or reactive current injection or absorption. And it's supposed to oppose the change on the grid. And all of them say that responses are expected within equipment limits. Some specifications specifically comment that there is a benefit if there is additional overcurrent capability or energy headroom, and if it's available, it would be advantageous to use it, but it doesn't require to oversize resources. There is only very high-level guidance about expected behavior at the limit. Some requirements have explicit sections on behavior at current limit, even though they don't go into much detail, it's still high level. But others only include requirements at the limit in the respective response requirements. I have a couple of slides with details on this one, and so I'll leave it out to you to look at it afterwards. It will be included in the deck. So counter imbalances. Fingrid requires to provide closed loop path for imbalanced current to flow, and there are additional side tests and high level acceptance criteria when measuring power quality during commissioning process. In other requirements, it says that grid forming should provide positive and negative sequence current to ensure that its internal voltage source is balanced during continuous normal operation and also during disturbances. And then grid forming should not actively oppose to flow of negative sequence current for small levels of voltage imbalance. So that's what Unify and MISO define. For harmonics, basically inverter can provide passive damping response for harmonic frequency range, thereby reducing harmonic voltage distortion. That's what AIMO advanced capability requires. AIMO also says that when providing this harmonic currents, there may be a capability to provide other grid forming functions is reduced. And so when sizing grid forming plant, one should think about it and think about background harmonics in the connection point. And then Unify specifically says that that harmonic distortion of voltage waveform produced by grid forming should comply with requirements at the connection point, and with that, maybe grid forming is helping to mitigate some of the harmonics on the grid, but there shouldn't be a requirement that grid forming mitigates harmonics on the grid just as a purpose. For damping, I'm kind of running out of time. I'll just very quickly go through this one and then jump to incentives slide. Basically, All of the requirements talk about damping. They define frequency ranges in which damping is important, and I believe this is based on phenomena that each grid operator is seeing on the grid. Additionally, National Grid ESO and VDE FNN define damping factor. Others just talk about providing damping in a certain frequency range. And then IEMO and MISO list the phenomena for which they're seeking provision of damping. I have some more details again on the slides, and you'll see it later. I'll jump onto incentives, I think, in the interest of time. There are also tests for short circuit ratio. So basically to ensure that the grid forming resource can operate stably at different short circuit ratios. There is a test that's defined by IEMO, ERCOT, and MISO. And again, you can look at it. Islanded operation. Again, stable operation is required when being part of an island without any synchronous machines and then reconnecting back to the grid. And then there is this loss of last synchronous machine test, and this one in IEMO and FinGrid, this is defined as possibility, so something that can happen, that grid forming inverter-based resources may end up in an island without any synchronous machines, while other specifications just looking at that as an ultimate test for grid forming capability, and it's not something that can actually happen in reality. And the tests are just to see how grid forming resource responds. I have a description of the test here on the slides. So again, you can look at it later. Black Start capability is something that defined in IEMO and Unify as advanced capability, and this list talks about what kind of additional capabilities are needed from resource to be able to provide Black Start. Okay, so I'll switch to requirements and incentives, and then just to leave some time for questions. So National Grid ESO, I guess, was the first one where they ran the Stability Pathfinder. So this was a series of tenders, 3, and then this phase 2 that they ran concluded in 2022, awarded 5 grid forming batteries that would provide this grid forming capability, and they need to comply with specifications for grid forming that National ESO has defined. And then, so the idea was to procure these first resources and kind of learn from this as they go. And then they followed with development of stability market. And so they developed eligibility rules, contract structures, procurement strategies for future stability market. And the midterm stability market launched last year already. And the idea here is that they procure extra levels of inertia that they need on the system, and extra levels of short circuit current contribution that they need at different buses on the grid. And so this is above what actually the resources that are already there are providing, and in addition to what Pathfinder already got them. And then in December 2022, Australian Renewable Energy Agency backed up 8 grid-scale grid forming battery energy storage projects. So basically, I believe it's 10% of the capital investment that Australian Renewable Energy Agency will provide as a subsidy. IEMO has also minimum system strength requirement in certain areas. And so basically, if you're building grid following inverter-based resource, it's seen as deteriorating system strengths in the area. And that provides extra motivation to maybe bring a grid forming battery next to this resource, or if it's a battery already, maybe build it as grid forming. So it's not a market product, but it's an extra incentive. And as I mentioned, IEMO specifications are voluntary at the moment. FinGrid currently only allows grid forming batteries to be built in weak grid areas. So this is kind of a bit of an incentive. And ERCOT looked at similar idea in the dynamic stability assessment study in 2018. But actually currently ERCOT, MISO and FinGrid are drafting requirements for all future batteries to be grid forming. So this will be a requirement once it is approved. ENTSO-E RFG also aims for requiring all future type B and D, B through D IBRs to be grid forming. And then again, kind of very recent, what I learned from a workshop last week is this German inertia market, where they're thinking of payment for new inertia to all resources fulfilling this latest VDE FNN specification. And it will be implemented in 2025. So just to provide a little bit more insight on that, as I mentioned, they are looking for 4 products. So it's positive inertia basic product. So that's basically responding to overfrequency events. To under-frequency events. Basic product is when it's available during 30% of the time. Positive inertia premium product if it's available 90% of the time. Negative inertia product is for over-frequency events. Again, basic and premium product, respectively, for 30% availability, 90% availability. And so the idea is whoever wants to provide this product, they have to go through testing and prove that they conform with this latest VDE FNN requirement. And in this test, it will also be kind of seen what kind of level of inertia that they can provide. And then they will say if there's 30% availability or 90% availability. The thinking behind this is that currently, system operators in Germany already have some measures that they install as on the transmission asset side to support inertia and system strengths. And so they are looking for this extra boost for this, momentary reserve service in the meantime, and also to boost this new grid forming technology, being a little bit more incentivized. And then by 2030, when ENTSO-E RFG is approved and it becomes a requirement for future IBRs to be grid forming, maybe then that becomes a requirement. So this is kind of to pilot this new technology to see what's capable of and incentivize installing it already today. A little bit about projects. Again, I keep a page on ESIG website with all this project and more. This one is only focusing on batteries, but I also have some HVDC projects there. If you go there and you see a project that is not mentioned there, please let me know. So you can see by year some of the grid forming projects that have been already installed. All of the projects backed up by ARENA that I mentioned just now in Australia, they are all under construction and are all in this list of projects. So there is more and more coming, and some of them are in hundreds of megawatts. So just to conclude and leave some time for questions, if inverter-based resources are built with grid forming controls, stability can be provided from resource itself, and maybe we don't need additional mitigation as from transmission assets. And so that can reduce overall costs of system operation and also allow higher shares of inverter-based resources. We can potentially go up to 100% in some areas. Grid code requirements and market products are needed for grid forming IBRs to be deployed in an efficient and timely manner. In my previous webinar, I talked that it took 20 years for Europe to develop grid codes for present day inverter-based resources. In the US, there is still not unified grid code that applies to all grid following inverter-based resources. And now we already have this grid forming resources coming in some areas. We don't have 20 years to figure out the requirements. So we need to work faster and maybe, harmonize it better than with the previous grid codes. Recently published grid forming requirements and specifications, they agree on high level functionalities that they are looking for, but there is still a lot of diversity in details. And I think it makes manufacturers' life very complicated and also developers' life very complicated, because every requirement is different and devil is in detail. And so every single parameter differs. That means that they have to develop different products for different markets, which makes it more expensive. There is a number of activities going on in the US and Europe and Australia to accelerate development of grid-forming IBRs, incentivize them through markets, but also some system operators are thinking about requirements. This challenge is broad and global because in the meantime, existing grid-following resources are continuing being built. There are more and more pockets with weak grid conditions, and so either we need grid-forming resources in those areas or we need additional transmission assets there. As we see more interest picking up in building batteries, we should think about grid-forming being a lower-hanging fruit for battery energy storage. And so maybe go for it first and seize this window of opportunity now and figure out how we do it for solar and wind, or if we even needed to do for solar and wind later on. So with that, I'll leave 10 minutes for questions.
Excellent, Julia. Thank you for that great presentation. Lots of questions. And thank you all for voting up some of the most important ones. This first one might be hard to answer exactly, but just I think looking more for a perspective and an opinion, Julia, approximately what are the differences in capital expenditures and operational expenditures, i.e. the cost between grid following and grid forming when it's coupled to the same system? Can you make any comments on that?
So the answer is it depends. It's overall people say, and then what I mentioned for batteries, and I'll probably only talk about battery because I don't know what it may cost for other types of resources. For battery energy storage, the considerations are primarily on software side. But there are still considerations. I have a really nice chart. I'll actually, maybe if I can, I'll include it in the deck if I have a permission from the author. There is a really nice chart from Fluence where they show how, if you're planning grid forming, you still have some considerations on state of charge you need to keep. Maybe you need to back down a resource and you cannot operate at full power all the time. So there is this lost opportunity that, you cannot use for energy. There are some studies involved that are different and some testing that is different, and none of it is free. So it's in a single-digit % of the overall project cost, but it's not zero. I think that's the point. And I think it's even like site-specific. That what we'll find, that it's not even just technology specific, it's site specific and depends on requirements for grid forming.
Yeah, I think you covered that well. It's definitely it's a depends answer. The next question is, do you see any ongoing benefit or need for battery energy storage in grid following mode, or do you believe that BESS will really converge on grid forming behavior altogether?
I mean, all the other revenue streams are still there for grid following, right? You can do arbitrage, you can participate in frequency response type of products. They can provide reactive support as any other grid following resource. I'm just seeing that with it being relatively low hanging fruit to make it grid forming, I just don't see why not. I see there is really this opportunity in the future for them to provide support for weak grid areas, but cost is probably not high. It's of course it's better if it's valued and if it's incentivized, then it's clear for developers that they should go for grid forming, and so maybe that's something system operators should think about, how to incentivize it. It's either it's a requirement and it's clear that all batteries should be grid forming, or it's a market, and then there is a clear value for it. So I mean, there is benefits. All these benefits for grid following battery are there as before, but grid forming is an added benefit.
Yeah, great. Thanks for that. The next one says grid forming is something that it's a question. Is grid forming something that we set in the inverter itself, or is it something related to the construction of the inverter? So I think the genesis is it a software setting, or is it a hardware capability, or both?
It's like in a battery. I mean, I guess like in the inverter is a control strategy. So it's not one setting, but it's a control loop that makes it behave certain way, either grid following or grid forming. But then behind that control, there is a source, which is, if it's a battery, is great because it has inherent energy storage. Whereas if it's PV or wind, then you need to think about where this energy instantaneously is coming from, which is not very straightforward and probably requires hardware changes.
Yeah, exactly. This next question, it came a bit early on, and I think you covered it somewhat in your final slides around incentives versus requirements. But they're asking, in your opinion, should grid forming be compensated as an ancillary service, or is it better to be mandatory and have a mandatory capability for resources like primary frequency response or VSS? Is there advantage or disadvantage of one or the other?
It's a tough one. I think I guess like incentives is always clearer and kind of easier, I guess, to implement than a requirement. And also it's easier to justify. You can also make it locational, whereas if you require from everyone, then maybe you end up with some kind of redundant capability in some places where you don't need it. I would say it's system specific, maybe for systems that are like island type of systems that are already struggling with low inertia and low system strengths. Maybe that is more, it's similar to like ORCOT, I like ORCOT example, and PFR. Somebody mentioned PFR, right? So for ORCOT, PFR is really essential reliability service that always needs to be there. They do have a market for a certain amount of reserve, but everybody has PFR capability, and so everybody will respond to an event based on headroom that they have. And so I think for an area like that, it maybe makes more sense to just require future resources, and especially batteries, to be grid forming. For some other areas where there is a lot of synchronous generation still, and there are just some weaker area pockets, it's more locational. Maybe something like tenders, something like national ESO is doing, is a better way. Because maybe you don't need it across the entire system just yet.
Yeah. That makes sense. The next, I'm going to combine a few questions here, because I think you answered one to a certain degree, and there's another similar one. More around the fact of, if you have a choice between grid following and grid forming, what would drive the incentives either way? And if you had a battery that can do grid following, grid forming together, can it be switched between grid following and grid forming, or is it primarily only one or the other? Can you comment on that?
So most of the requirement actually is looking for no switching between grid following or grid forming. It's basically, as far as I understand, I'm also not an SME on this, but as far as I understand, you need two different controls implemented on one resource. And then you switch between these controls, and that may not necessarily be seamless for the grid that switch. And also, I don't see, if you have grid forming capability already, why would you need to switch back to grid following? It's only maybe like for testing, for pilot projects in the beginning. That's where I can see maybe some value. But overall, like if you look at the requirements, they all either require no switching or they recommend no switching, and you can see it in the slides. I have it there on some of the slides. So basically, no, I don't see value of having both controls there. And I'm thinking, if it's a battery, it makes more sense to think about grid forming with the way the industry is heading.
Yeah. Okay, great. We'll wrap up with one last question, and I think you answered the next one in the queue, with one of your last slides on markets. So maybe we'll skip over that one around any market incentives in the continental US that might be in place. But I'm going to also squeeze in the last question about grid forming specifications. Do they make any differentiation between resources connected to the transmission network versus the distribution network? Is there any examples there of grid forming on distribution?
So the only one, and I might have missed because my focus primarily was on transmission level specifications. The only one that talks about distribution level is ENTSO-E RFG 2.0, because it's requirements for all generators, so it includes down to very small generator types or generator sizes and down to distribution voltage levels. And so in that, they have requirement for even those resources to be grid forming, but it's left to national level to decide if it's going to be a requirement or not. So basically, they specify what grid forming on that level mean, but as far as I understand, as of current draft, the intention is it's not enforced at the European level, and at national level, it will be decided as needed.
Okay, great. Yeah, thanks. Thanks for giving that overview. Okay, we're about the top of the hour, so we'll wrap it up here. Really want to thank Julia for a really timely webinar and great insights onto the future of these grid forming requirements. As I mentioned earlier, an email will go out once the video file has been posted, and we'll be happy to answer all your questions that we didn't get to, and there are quite a few of them. And we'll get those back and posted as quickly as possible. We appreciate all your engagement and really look forward to seeing you again next week at our Fall Technical Workshop in Providence. We have another ESIG webinar coming up a couple of weeks on October 28th, covering ENTSO-E's grid stability initiatives. And further information on all of our webinars and meetings can be found at our website at esig.energy under the Events tab, and in our newsletters and informational emails. And you're all invited to attend. Thank you once again, Julia, for this great webinar. And thank you all for your interest. Really look forward to seeing you again. In the meantime, have a safe trip. Have a safe day. Thanks for all your participation, and see you soon. Good day, everyone.
Right. Thank you. Yeah, and just one more thing to mention, if you've seen something, I missed the project, I missed the requirement, please let me know. I'm always looking for more documents to look at. Thank you.
Thank you all.